All right, welcome to the second video on electric potential. In this video, we're going to generalize some of the things we brought up in the first video on electric potential. We're basically doing the first half of chapter 26 in this video. The next video, we'll do the second half. So we're talking about everything related to electric potential before capacitors. So this video will be this stuff. And then the last few things about capacitors will be the next video. There's not all that much new in this video, other than like it's a little bit more mathematically sophisticated ways of saying things that were brought up in the last chapter. So the first couple sections are all about the relationship between the electric field and the electric potential. And this basically falls under two categories. So we're not going to talk about these two. We're just talking about the electric field and the electric potential. No forces, no energy here. So basically, we want to study these two, like going each direction. So you could be given the electric field and you have to calculate electric potential difference, and that's this first formula. Or you could be given the electric potential and you have to calculate the electric field. So that'll be the formula given in the next section. And so the key thing is that the relationship between these two things, the electric field and the electric potential, is that one is the integral of the other. So basically you have electric field, maybe I'll do potential up here and field down here. To go this way, you take a derivative. It's minus a derivative with respect to position. And to go this way, you integrate with respect to position. Integral dx. I'm choosing x here, but it could be, it depends on the parameter introduced in the problem. That's the gist of it. I mean, there are some subtleties because really this is there's a multi-dimensional relationship between V and E, but we're not talking about gradients and everything in this class. So we're going to simplify, so I want to describe the ways in which we're simplifying in this book. So, okay, the first formula, this one right here, focuses on if you knew E, how do you find V? So starting here, how do you find V? And the answer is, well, you integrate. So the integral of the electric field you can use to find the electric potential. And you have to remember this minus sign, because remember, if you're integrating along the electric field, if you're summing up the electric field in the same direction as the electric field, then the electric potential goes down. So if you're integrating E along E, then you have to stick in this minus sign. Well, you always have this minus sign, but you need the minus sign because the electric potential goes down in that case. And if you're integrating with E opposite, or along a direction that's opposite E, then integral E dot ds is negative, and with this minus sign here, your delta V is positive. So your book does an example of this. Again, given E, so you're given the graph of Ex as a function of x, and you're asked to find the potential as a function of x, and you do minus the integral. So here it's a linear function. The integral of that is a parabola, is a quadratic function. And the integral of this would be a concave up parabola, but this is concave down because of that extra minus sign. So really, this is a multi-dimensional statement about requiring the dot product between those two things. A lot of times we'll just say the electric field is along a certain direction, and we'll just focus on that one direction, and we'll integrate along that direction. So we'll try and make this as easy as possible. So using this, we can prove a result that we already know. We know the electric field due to a point charge is kq over r squared, and we can use our formula from before to use that fact to show what the electric potential is due to a point charge. But we already know it's kq over r. So it's just thinking of it a different way. So you got to be a little careful with the minus signs here, but using the 0 at infinity being the electric potential at infinity being 0, so requiring that fact, we can, instead of talk about delta V's, we can talk about just V by itself, right? So another example here. This is the other way. So this is, if you start with electric potential, how do you find the electric field? And it's minus the derivative. So this is if this derivative is along the direction of the electric field. So remember that, like, if you have an equipotential surface, the electric field is perpendicular to this, right? So if the potential is say the potential is 10 volts here, and if this is the electric field direction, the electric potential has got to be decreasing along that. So maybe this is 0 volts. So 0 volts and negative 10 volts. And electric field is perpendicular to the equipotential, right? So keep in mind that, like, if you go from this point to this point along this path, you're going along the equipotential, and there's no change in the potential if you go along that path. So like you start at 10 volts, you end at 10 volts, the delta V is 0. So like dVd along that path to the right would be 0, but the electric field is obviously non-zero here. So this formula is assuming that you're taking a derivative along the direction of the electric field already. So E depends on how quickly the potential is changing, is the point right here. So imagine you had potentials that were like that, and then all of a sudden they started to bunch together. And they got really, really close right here. So this is 20 volts, 30 volts, 40 volts, 50 volts. What this formula is saying is that the closer together those potentials are, the bigger the electric field, right? So right here, point right there, the electric field is much bigger than the electric field right here. And a way of, and remember that the units of E are volts per meter. So units of E, volts per meter. And again, that's, you can see from this formula, it's volts per meter. And so what you can do is you can estimate the electric field by saying, well, okay, we have 10 volts here and negative 10 volts here. This is about minus delta V over delta X. So the delta V from those 2 points would be 20 volts in magnitude. And then the distance would be whatever this distance is here. But right here, if we look down here at the bottom part of this diagram, it's the same 20 volts, but it'd be a much smaller distance. And so if you plug in a much smaller distance here, you get a much bigger electric field. All right, so again, this is if you know something about the potential. So imagine you already knew all the dotted lines and how close they were together and everything. You could actually quantitatively get the electric field by delta V over delta S, but you have to be going along that direction. Because remember, like if you go left, right, in this picture, you're not changing potential. You have to already be going in that perpendicular direction to use that formula. So we're actually going to talk about that one in class. And so all of these examples are given V, find E. So given V, E is the minus derivative of this. So this is a positive constant slope. And with this extra minus sign, it's a negative constant electric field. And yeah, this is visually what's going on. So I already kind of described this previously. Kirchhoff loop law. So if you start at some point, you can track delta V's just by adding them up. So from point 1 to point A, you're going along the equipotential. There's no change in voltage. So that's 0 volts voltage potential difference between those 2 points. So 0 volts, and then we go up 20 volt or 10 volts from 20 to 30 volts. So we go up. So our delta V is 10, and then 0 more, and then 10 more, going from point C to point 2. So overall, our change in voltage is 20 volts. But then if we go back to 1 along that path, we're going back to our starting point. We decrease 20 volts again. So this is just the statement that if we go in a loop back to our original point and we sum up all the potential differences from start to end, we get 0. That's called Kirchhoffs loop law. It'll be very useful when we talk about circuits. Conductors and electric potential. Remember that the electric field was 0 inside a conductor. And remember the relationship. So if we know E, how do we find V? Well, that was this formula, minus the integral of E dot ds. So if we know that E is 0 everywhere inside a conductor, and we integrated 0 from one point inside the conductor to another, so this picture has point 1 to point 2, we're integrating 0, we get 0. So delta V from one point inside a conductor to another is 0. Which means V is constant. V is constant inside a conductor. So everywhere on the piece of metal is at the same electric potential. Right? Not only on the surface, but also inside the whole interior of the metal. They all have the same constant value of the electric potential. We don't know for a fact that it's 0. It's just any constant. It could be 0, it could be some other non-zero thing. So here, 0 volts everywhere on the surface and inside this one, 50 volts everywhere on the surface and inside this one. And in the region in between the conductors, you'll gradually go from 50 down to 0. So these equipotential surfaces actually match the shape of the conductor near the conductor, but you have to, like, to go from a circle to a straight line, you kind of have to gradually shift from the circle to a straight line. So you can see how the dotted lines, how they do that. And then once you have that, and that's actually easier to measure with a voltmeter, you can measure these equipotential surfaces, you draw it on a sheet of paper, and then you can infer what the electric field is, because the electric field needs to be perpendicular to all of those equipotential surfaces. Sources of electric potential. So a charge separation creates a potential difference, and this is going to be all about capacitors, which we'll talk about in the next video. Capacitors can store energy, but they very quickly, like if you use it as an energy source, you deplete the energy pretty quickly. When we talk about capacitors, you can, like, they used to, or your flashlight, or I guess in old school cameras, when you used to take a picture, you get a burst of energy, a big flash of energy, and that's due to a capacitor, and it will give off all its energy pretty quickly. In contrast, a battery has as its source of energy, it's charge separation, but there's some mechanism that's replenishing, like the charge separation. So it's basically chemical reactions inside a battery that maintain a relatively constant potential difference. So like 1.5 volts for a lot of batteries that you're used to, AA, AAA batteries. It's able to maintain a potential difference of 1.5 volts. So whatever potential it is at the negative end, the positive end is 1.5 volts higher than that. And the chemical reactions are able to maintain this constant, and over a very, very long time, maybe after 1 year, and your battery doesn't work anymore, it's like 1.2 volts. So you can actually take a voltmeter, and at 1.2 volts, it starts to not really function properly in whatever electronics you have. But batteries are much more longer lasting than capacitors because there's something actually forcing the charges to remain separated. And your book mentions that it's basically like having an escalator. So there's some energy source that's physically separating the charges always. And the escalator is like a constant source of energy that will lift you against gravity, right? And then you could just, you can put batteries together to get bigger voltage differences, but you have to put them in this order, right? Negative to positive for, like if you go from 0.1 to 0.2 to 0.3, you gain electric potential difference. So delta V is positive going from 1 to 2, and then delta V is positive going from 2 to 3, and you can add those two changes to get the overall voltage change from 1 to 3. Right? So like for the stop and think, so we're gaining 3 going from there to there, and then we lose 1. So overall we've gained 2, and then we gain 3 again. So it looks like the overall delta V going this way, delta V is 5 plus 5 volts. So generally you want to add batteries, negative to positive, and then negative to positive, if you're stringing together a series of batteries. And that's why if you put batteries together, like on the back of your calculator, a lot of times they're opposite because the top side's connected by metal. So this is the way that like the negative side of one battery is touching the positive side of another. So you kind of have this string like this. Okay, so the example problem. So remember, a big point of today is that, given either E or V, you can solve for the other one. So here we're given V, and we're asked to solve for the electric field. So that'll be part B. And the formula that we want to have in mind, so given V, we want to solve for E, and the formula is E is minus the derivative of V. Along, you have to be along the electric field direction, but as long as you do that, it's this formula. Okay, the electric field in a region of space is described by that function. Draw some equipotentials. Okay, so at x equals 0, so it doesn't say what region we should look at, but let's look at positive and negative x just to see what's going on. So I have in mind that we're going to draw, so this will be our number line. This is x equals 0. This is positive x and negative x. So this will be 1, 2, 3. It looks like these are all SI units. So -1, -2, -3. Okay, so equipotential surfaces. So at x equals 0, that's 0 volts. So it looks like we have, oops, let's draw this in red. So this will be our 0 volt equipotential. And then at x equals 1, it's 2 volts. So x equals 1, this will be our 2 volt equipotential. And even at x equals -1, we're at 2 volts. So this is a little, you gotta be a little careful here because we're not going from -2 to 0 to 2. We're going 2 down to 0 and then back up to 2. And then, so I've already drawn that the spacing between my equipotentials is 2 volts. So the next equipotential I draw has to be at 4 volts. So where is V equal to 4? Looks like it's at x equals square root of 2. Right? If x equals square root of 2, then we get 4 volts. So they start to bunch up more. So it looks like I made a mistake by doing it every 2 volts because they're just going to bunch up more and more and more. So there's 2 volts. Let me scoot this over, 2 volts and then 4 volts. And then the next one's at 6, which is at square root of 3. And it should be bunching up more. So maybe I didn't draw this quite accurately, but they start to bunch up more and more and more. At x equals 3, we have 18. So we're going to have a whole bunch of dotted lines in between. So let me just draw the fact that they're starting to bunch up. That's the main thing that I want to get at here. Some representative electric field vectors. Well, there's no electric field there, and then if the equipotentials bunch up, then the electric field is going to grow in magnitude. So the electric field vectors get bigger and bigger, and they're always going towards the direction of decreasing electric potential. So I don't want to draw in that direction. I want to draw them in the other direction, from 2 volts down to 1 volt. So it looks like the electric field is pointing in the negative x direction if x is positive. And it's pointing in the positive x direction if x is negative, right, to go towards the region of decreasing electric potential. So that's part A. Part B, what is the electric field at x equals 2? Well, we're going to use this formula right here. So we have our potential function, and if we take minus the derivative with respect to x in this case, x is going to be labeled in the coordinate. So s is just sort of a general label, but here it'll be x. So for part B, Ex is minus d, this function of x, dx. And the derivative of 2x squared is 4x. With a minus sign, it's minus 4x. And so that's Ex as a function of x. In particular, at x equals 2, we get -8. And that'll be volts per meter is the units for electric field. So if everything's in SI units, it'll be -8 volts per meter. And this tracks with our picture, right? If you look at x equals 2, the electric field is pointing in the negative direction, negative x direction. So it looks okay. You know, the signs seem to work out. Right?